Assalamualaikum. Welcome back to Sir K Lab's Physics and Chemistry tutorial for high school students. In today's episode, we interpret a phase diagram for the substance water. The phase or water phase diagram is a pressure temperature diagram that represents various water phases, including liquid water, steam, and ice under different conditions. So just hang on, watch, and learn. The pressure temperature graph shown in this figure is called the phase diagram for water. This graph is not drawn to correct scale. This is to accommodate several important characteristic properties of water at a glance. All right, so this liquid vapor curve, BC, the curve that is now being highlighted, this curve separates the liquid and gaseous regions of the phase diagram, all right? And it also provides the boiling point for water at any pressure. For example, at 1 atmosphere or 101 kilopascal, the boiling point is 100 degrees Celsius. Now, this curve BC, also shows that water can also boil at temperatures lower than 100 degrees. All right, if the atmospheric pressure is less than 101 kilopascal or 1 atmosphere. Notice also that the liquid vapor curve BC, terminates at a temperature of 374 degrees Celsius and at a pressure of 218 atmosphere, that's equivalent to 22,089 kilopascal, indicating that water cannot exist as a liquid above this temperature, regardless of the pressure. The physical properties of water under these conditions are intermediate between between those of its liquid and gaseous phases. This unique state of matter is called a supercritical fluid. The solid vapor curve, labeled AB in the figure, indicates the temperatures and pressures at which ice and water vapor are in equilibrium. These temperature pressure data pairs, all right, correspond to the sublimation or deposition points for water. Sublimation, as you may all know, is the phase change from um, solid to gas without passing the liquid phase, while deposition is exactly just the opposite, all right, from gas or gaseous state to the solid state without passing the liquid state. Now, if we could zoom zoom in on the solid gas line in the figure, we would see that ice has a water pressure of about 0.20 kilopascal at a temperature of negative 10 degrees Celsius. Thus, if we place a frozen sample in a vacuum with pressure less than 0.20 kilopascal, ice will sublime. This is the basis for the freeze-drying process often used to preserve foods. The solid liquid curve or line labeled BD shows the temperatures and pressures at which ice and liquid water are in equilibrium. This line represents the melting or freezing points for water. Note that this curve exhibits a slight negative slope, which is exaggerated here for clarity. This indicates that the melting point for water decreases slightly as pressure increases. At standard pressure of 101 kilopascal, the freezing point of pure water or the melting point of pure ice is exactly equal to 0 degrees Celsius. Now, these freezing or melting points decrease slightly if the pressure uh, is increased. All right? So, water is an unusual substance in this regard, as most substances exhibit an increase in melting point with increasing pressure. The point of intersection of all three curves is labeled here as point B. All right? At the pressure and temperature represented by this point, all three phases of water coexist in equilibrium. We call this point the triple point. So at pressures lower than the triple point, water cannot exist as a liquid, right? Regardless of the temperature. Now we're ready to answer uh, some questions. Question number 1. From the phase diagram for water, determine the state of water at the following conditions. Letter A, 35 degrees Celsius and 85 kilopascal. Letter B, 75 degrees Celsius and 3 kilopascal. Letter C, negative 15 degrees Celsius and 0.1 kilopascal. And letter D, 200 degrees Celsius and 50 kilopascal. Question number 2. What phase changes will take place when water is subjected to varying pressure at a constant temperature of 0.005 degrees Celsius, at 40 degrees Celsius, and at negative 60 degrees Celsius. So for question number 1A, what is the state of water at a temperature 35 degrees Celsius and pressure 85 kilopascal? Alright, so we just locate in the graph where these quantities intersect. all right, as highlighted here now. So, water is uh, in liquid state at these conditions, all right? Uh, 35 degrees Celsius is approximately at this point, all right? While 85 kilopascal is estimated to be at this point. So when they intersect, all right, the two broken lines intersect at that point, all right, which falls in the region of uh, the liquid phase of water. So that's how we arrive at our answer for letter A. Now, for letter B, at a temperature 75 degrees Celsius and pressure uh, 3 kilopascal, all right? So doing the same method or technique, all right? So we find the temperature 75 degrees Celsius to be at this point, all right? While 3 kilopascal is at this point in the y-axis. So when they intersect, all right, the point of intersection is in the region of uh, the gas state. Therefore, our answer to question letter B is that water is in gaseous phase. At the temperature um, negative 15 degrees Celsius and pressure 0.1 kilopascal, that's for question letter C, right? We say that water is in solid state, all right? As shown in this uh, diagram, we have highlighted the point of intersection of the two quantities, all right? So we estimate that the temperature is at this point, negative 15 degrees Celsius, while the pressure 0.1 kilopascal is probably at this point. So they intersect at a point which falls within the uh, solid phase or state. All right. So that's for question letter C. And the last question for letter D, the conditions are the temperature is 200 degrees Celsius. So in our graph, that's approximately at this point. All right. So the highlighted broken line, all right, is drawn vertically, while the pressure 50 kilopascal is approximately at this point in the y-axis. So the two highlighted horizontal and vertical dashed lines intersect at a point falling within the gaseous phase of water. That's why our answer is that the state of water is gas at these conditions. So for question number 2, we are asked to identify the change of state of water at specific temperatures, such as for letter A, at a temperature equal to 0.005 degrees Celsius, all right? So in the figure that's now being highlighted by this broken line, so we estimate that that temperature is somewhere here, all right? in the temperature axis. So we draw this broken line vertically up, all right? And you will notice that at this temperature and at a pressure that's lower than 0.6 kilopascal, all right, we have the first or initial state of water being a gas, all right? So, based on our broken line representation, all right, as the pressure is increased, all right, above 0.6 kilopascal, so it passes through the state of being a solid, and further increase in pressure, all right, way above 101 kilopascal or 1 atmosphere, we find this broken line, all right, passing through the liquid state of water. And so therefore, our answer to question letter A is that water changes from initially gas, then to solid, and then finally to liquid. All right? Next, for letter B, how about at temperature of 40 degrees Celsius? So 40 degrees Celsius, as shown in our figure, is now being highlighted. It is approximately at this point in our temperature axis, all right? So as the temperature or as the pressure increases, all right? Notice that initially the gas is, the state of water is a gas. Then, at a higher pressure, higher than 0.6 kilopascal, all right, all the way to 22,089 kilopascal, you'll notice that water, okay, undergoes a phase change from gas to liquid. So our answer is water changes from gas to liquid at this fixed temperature 40 degrees Celsius. And for letter C, when the temperature is at negative 60 degrees Celsius, in our figure, that's approximately at this point in our temperature axis. And as we increase the pressure, all right, notice that initially water is already in its solid state, all right? And as we increase the pressure, all right, notice that the broken line only passes through the region for solid state. In other words, our answer to letter C is that water does not undergo any phase change, all right, at such a very low temperature, all right? So at a very low temperature, like this, negative 60 degrees Celsius, and a very low pressure, water exists as a solid. Increasing the pressure at such very low temperature keeps water in solid state, all right? Even if the pressure is, or even if the pressure increases. So that concludes our tutorial for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.